Hello, Roz. For lesson 2.1 on using set notation, I want to take a look at 4 quadratic inequalities. In our lesson, we discuss some of the issues with solving inequalities, the idea of the placement of the plus or minus symbol and the logical either fallacies or truisms that we need to find. I just want to stress once again how simple these questions can be with a quick sketch. For all 4 of these, notice that I'm interested in comparing x squared to some value. It happened to be the value 25 or its opposite. So what I'm going to do for all of these questions is set f of x to be x squared. Let's make sure we understand x squared is not a parabola. X squared is not a quadratic function. If I want to solve this graphically, I need to introduce a graph. Then what I'm going to do for each one of these questions is draw a sketch of my function, y equals x squared, or f of x equals x squared. I'll label it. And then I want to know, I'm translating this question into when is a parent quadratic above a height of 25? So here's a height of 25, and that's a height of 25 because I say so, once again. On my sketch then, I can already anticipate that I'm going to have 2 different solution sets here. Sometimes students try to memorize based on the direction of the inequality if you're going to be double-ended or double-sided, and it's not worth it. Just look at your sketch. I think from your sketch as well, you could probably figure out that when x is 5, your output will be 25. And then because of the symmetry of the curve, here's an x value of -5. So here are our solutions in one dimension, any x value that is greater than 5 or less than -5. And here's our solution in set notation. Our solution is the set of all x values such that -5, whoops, sorry, I'm going to change order here and say x is either less than -5 or, pardon me, x is greater than 5. And x is any real number. And I'm running into the room that I'm going to use a little bit for question B. But I guess in question B, I could use the same sketch. I think I'm just going to draw a new sketch here. By looking at the sketch, I don't need to worry about the placement of my plus minus. I don't need to worry about any sort of restrictions that occur when I square. I don't need to worry about the logic, which we don't have a lot of practice with. It gives me a reason to practice sketching. Here's the curve f. Here's the height 25. I want to know when am I on a height of 25 or lower than a height of 25. I see that that happens over this interval. So not outside of -5 or +5, but between -5 and +5. And I'm using the solid dot for the inclusive case here. So my solution to this equation is going to be, or my solutions, there's an infinite number of them, my solution set, I could use that in the singular. It's going to be the numbers between -5 and 5, inclusive, all those real numbers. Okay. Notice there's really just one statement here. That's because there's one interval. Here I need 2 statements. I cannot write this as -5 and the alligator wants to eat the x and the alligator wants to eat the x and 5. This is nonsense. This means that 5 would actually be less than -5, and that's not true. Okay, the reason why you need 2 statements here is shown on your graph. You have 2 different arms. Each arm gets its own statement. Okay. What about these 2 cases? This is where, when students work algebraically, they get into all sorts of trouble. And if we're not working algebraically here, the question should be, or sorry, the answer should be almost obvious. I don't like using that word because if it was obvious, you wouldn't need my help to do it. But let me help you realize that it's obvious. I want to know, when is my curve below the height -25? The answer is never. The output of a square is never going to be lower than -25. So I think I would say there is no solution, and that would be my conclusion here. Okay. You could try to build a set that has a contradiction in it, but sometimes just writing it in English is best. Don't leave it blank, because then your reader doesn't know if you understand that there's no solution or you don't understand the question. But yeah, just conclude in English. Please don't say x equals does not exist or x equals no solution or something silly like that. Let's try D and see if it seems silly as well or obvious as well. X-axis and y-axis. Not a bad idea to label your x-axis and y-axis when you have a horizontal line in there, so we can tell them apart. Here's my parent quadratic. I will label it. That's f, whose outputs are the square of x. And I want to know when is the square of a number greater than or equal to a negative number. Well, the square of a number, a real number, is going to be positive or neutral. So when is it greater than a negative number? Always. Now this one, you could try answering in English, but I would like you, specifically given these directions written in set notation, I want you to try to write it as a set. It's the set of all x's, as long as x is a real number. There's no restriction on here. The restrictions in your set actually reduce the number of solutions. This right here is saying x can be any real number, and that's how you would conclude there. Okay. We are going to be using sketches very often in this course and in other courses to help us spot solutions. And there seems to be an aversion by students. They don't want to sketch, and I'm not sure why. Maybe some students feel like it's not academic enough, it's not robust enough. This is a post-secondary strategy that you will be using. I think some students don't want to do it because it takes a little bit of time, but I would argue that it's worth it. So try it.